Hello, I'm Professor Afshar at Glendale Community College. This is Physics 101, Lecture 28. In this lecture, we'll discuss the work-energy theorem and conservative forces. These topics are covered in Chapter 7 of our textbook by Surway and Jewett. We start this lecture with the work-energy theorem, which states that the total work done on a system is equal to the change in the kinetic energy of this system. So remember what kinetic energy is. Kinetic energy is the energy of motion. Here we're talking about the change in kinetic energy. So delta K here is really referring to K final minus K initial. And of course that will equal to 1/2 mv final squared, the kinetic energy of the system, minus 1/2 mv initial squared, which is the initial kinetic energy of the system. According to the work-energy theorem, this change in kinetic energy must be equal to the total or net work performed on the system. Also remember that if there are 7 different forces acting on a system, then there are going to be 7 different works. In other words, each force performs its own work, and W net refers to the sum of all of those works. Now, I don't normally test you guys on the derivation of concepts. However, I do think that derivations are important. By studying derivations, you first of all learn the scope of a formula, so you learn when it's appropriate to use the formula and when it's not. And also derivations test your mathematical skills, and they remind you of both math and physics facts that maybe you have forgotten. So in this case, we'll go through the derivation of the work-energy theorem as a useful exercise. To begin with, recall that work is force times distance. A little more precisely, work is the integral of force times distance. Here, just for the sake of simplicity, we're imagining that whatever our system is doing, it's doing it in the x direction. So we're imagining that the object is moving only in the x direction, and therefore we're integrating relative to x. We are interested in the net work, and therefore we need to integrate the net force. If we're interested in the work done by friction, then we would integrate the force of friction. If we're interested in the work done by gravity, then we would integrate the force of gravity. For net work, it must be the net force. Recall by Newton's second law of motion that the net force acting on a system is equal to mass times acceleration of the system. So I'm going to replace F net by ma. Then recall that acceleration is the derivative of velocity with respect to time. Acceleration tells you how much velocity is changing relative to time. So I'll replace a with dv dt. Now, although dv dt is a derivative, we can treat it as if it's a fraction and transfer the dt to the dx, transforming this integral to m dv dx dt. You can justify the same step using the chain rule, but that's probably unnecessary here. Now we recognize dx dt as the definition of velocity, so I'll replace dx dt with v, and now have the integral of mass times velocity dv. Mass is a constant, you can bring it out. Integrating v gives you v squared over 2. So now we have 1/2 mv squared. This should already look familiar to you. This is kinetic energy. Of course, we don't want to forget about the limits of integration. So we have to plug in the limits of integration, initial velocity to final velocity. When we do that, we find 1/2 mv final squared minus 1/2 mv initial squared, which is exactly delta k. So we find that quite generally, regardless of what the system is or what forces are acting on it, the total or net work on it is always equal to the change in the kinetic energy of the system. Now, this formula by itself does not seem very important, but trust me, this is an incredibly important equation because in our next couple of lectures, we will use this equation to derive an extremely important result in physics. We will use this equation as the foundation for the concept of conservation of energy. Let's do a practice problem involving the work-energy theorem and the concept of work more generally. A block of mass 3 kilograms, initially at rest, is pushed a distance of 6 meters along a floor with an applied force of 25 cosine x squared. Notice the force, the applied force, is quite complicated. The block's final speed is 6 meters per second. The coefficient of friction between block and the floor is 0.1. Calculate the total work done on the block. So there's a lot going on here. We have a block, its mass is given to us. Initially, the block is at rest. So this particular phrase here tells us that V initial is equal to 0. And the block's final speed is 6 meters per second. So we also know the final velocity of the block. It's pushed a distance of 6 meters along the floor, and during that time there are multiple forces acting on it. Gravity is pulling it down, the normal force is pushing it up, there is friction, so friction is resisting the motion, and of course there is this applied force. So like imagine a person is pushing this thing, and the force that the person applies is a variable force, 25 cosine x squared. So it's a force that goes up and then comes down in a periodic manner. We want to calculate the total work done on the block. Turns out there are two ways you can answer this question. The hard way, or the long way to answer this question, is to calculate each individual work and then add them together. So for example, we can say the work done by the applied force, that's this FA, is the integral of the force with respect to dx. So now we have to integrate 25 cosine x squared. The limits of integration are 0 to 6 because we're pushing the block 6 meters from x equals 0 to x equals 6. You may want to look up how to integrate cosine x squared. Hopefully this is something you remember from your calculus class. If you actually evaluate this integral and plug in the limits of integration, you find that the work performed by the person that is applying this force is approximately 71.6 joules. Of course, there's also friction. The coefficient of friction is given to us, so we can also calculate the work done by friction. The work done by friction is equal to the integral of the force of friction, integrated with respect to x. The force of friction opposes the block's motion, so it points in the opposite direction, in the negative x direction, we could say. Hence, there is a minus here. And remember how we calculate the force of friction. It's mu times n. N is going to be equal to weight, mg. So we now need to perform this integral here. Mu, m, and g are all constants. You can bring them out of the integral. The integral of dx is just x. You plug in the limits of integration, 0 to 6, and you find that the work done by friction is approximately minus 17.6 joules. Notice that the work done by friction is a negative number because friction is resisting or impeding the motion of the block. The block is moving one way, friction is pointing in the opposite direction. If you think about it, you can convince yourself that the work done by weight is 0 and the work done by the normal force is also 0. So we're finally ready to calculate the net work. The net work is the sum of the works that you see here. So add 71.64 to minus 17.64, and you will find that in this case, the net work performed is 54 joules. This is the hard or long way to calculate the answer. A much easier way to calculate the answer is to use the work-energy theorem, which we were just talking about. According to the work-energy theorem, W net is simply equal to delta K, the change in kinetic energy. We know that initially the object was at rest, so its kinetic energy was 0. And then finally it was going at 6 meters per second, so its final kinetic energy, 1/2 mv squared, can be calculated easily. and it comes out to be 54 joules. So the net work is equal to 54 joules. Both methods give you exactly the same answer, but obviously the second method, using the work energy theorem, is a lot more convenient. Next, we want to discuss the concept of conservative forces. However, to understand conservative forces, we first need to do a couple of practice problems as examples. So here's our first practice problem. A crate of mass 50 kilograms is to be lifted to a height of 7 meters. Calculate the work done by gravity along each of the two paths shown below. So what we have is a crate that's initially on the ground, and we want to lift it by 7 meters. We can do this in two different ways. The simplest thing to do is to lift the box directly 7 meters along this green path. But another way to do the same thing is to move the box horizontally by 10 meters, lift it by 7 meters, and then move it back horizontally by 10 meters again. It's not really so important why you're doing this, but you can imagine that you're working in a warehouse maybe, and you're trying to possibly use a forklift to lift a heavy object to a top shelf. And you can do this via a direct path, but maybe there's an obstacle in your way, so you decide to move the object some distance to the right, lift it, and then move it back in. Or this is the kind of thing that might happen if you're trying to move into your new apartment on the second floor. If this crate contains your piano, you may not be able to lift it directly from street level to your second story apartment. Instead, you might have to carry the piano crate down a hallway, get it inside an elevator, raise it by 7 meters, and then carry it back down the hallway on the second floor to your apartment. Anyways, the details of why you would want to do this is not so important. For now, we just want to calculate the work as we move the object along the green path, and then we want to calculate the work again as we move the object along the blue path, and we want to compare those two works together. We are focusing on the work done by gravity. We're not interested in the work done by friction or by the person who's actually carrying the crate. We're specifically focusing on gravity. To calculate the work along the green path, we can proceed as follows. So the work done by gravity is equal to the integral of force times distance. Remember that we're talking about a dot product here. Remember that the dot product of force and distance is the magnitude of the force, so that's mg, times the distance, that's dy, times cosine of the angle between the force and the displacement, which in this case turns out to be 180 degrees. Remember that if you're moving along the green path and the block is, let's say, over here, then the force of gravity is going to be pulling it down. So this is weight, or the force we're interested in, and the displacement vector is going to be going up, since we're moving upwards, since the velocity points upwards. As you can see, the angle between these two vectors is 180 degrees. We need to evaluate the cosine of 180 when we evaluate the dot product. And you hopefully know that cosine of minus 180, or cosine of 180, is minus 1. Mass is given to you. G, of course, is 9.8. Don't forget the limits of integration. When you evaluate this, you find that the work done by gravity along the green path is minus 3,430 joules. Now let's do a similar calculation for the blue path. The blue path is more complicated. We have to divide it into 3 stages. Stage 1, we're moving the box horizontally. Stage 2, we're moving it vertically. And then during stage 3, we're moving it horizontally again. So I'm going to perform 3 integrals here. During stage 1, the displacement vector will point horizontally. So if the box is here, the displacement vector will point like this. And the force vector, weight, will point straight down. And as you can see, the angle between these two vectors is 90 degrees. So for stage 1, I need the magnitude of the force vector, I need the displacement vector, and then I need the cosine of the angle between those two vectors, which is 90 degrees, and of course cosine of 90 degrees is just 0. For stage 2, I'm lifting the box vertically, so the displacement vector points upwards like so, and weight, as usual, points downwards, and the angle between these two vectors is 180 degrees. So I have the magnitude of the force, I have the displacement vector, which now points in the y direction, and we have cosine of the angle between those two vectors, which is 180, and of course that equals to -1. For the third stage, or the third leg of this trip, we're moving the box to the left, so the displacement vector looks like so, and the force vector or weight will point straight down, and as you can see, the angle between these two vectors is 90 degrees. Remember, when we measure the angle between two vectors, we always take the smallest positive angle between them. That's our recipe or procedure for calculating angles. So for the third stage, we have the integral of magnitude of the force times the displacement times cosine of the angle, which is 90 degrees, which of course gives us 0. You can evaluate each one of these integrals. Two of them, of course, will immediately end up being 0. And so what you have is that the work done by gravity is minus 3,430 joules. Notice that although the blue path is considerably longer than the green path, the work done by gravity is the same for both paths. The work done by friction would be different. The work done by the poor person who's pushing or carrying this heavy crate is going to be different, but the work done by gravity appears to be independent of the path. For a long path and a short path, gravity performs the same amount of work. Remember this result. We'll come back to this result in 2 slides. Here's our second practice problem. A crate of mass 50 kilograms is to be moved a distance of 10 meters across the floor of a warehouse. The coefficient of friction between crate and floor is 0.2. Calculate the work done by friction along each of the 2 paths shown below. So imagine that you're operating on the floor of a large warehouse and you're interested in moving a box from some initial position over here to some final position over here. You can move the box along this direct green path. This is probably the easiest way of doing it. However, you might imagine that the direct path is blocked by some obstacle, so you might have to go around that obstacle, in which case you might move 7 meters horizontally in the y direction, and then move 10 meters horizontally in the x direction, and then 7 meters back to get to your final destination. Notice in this example, we have a top view of the warehouse, so the x and the y axes are both laid down horizontally on the ground. So all motion is horizontal motion, but some of it is in the x direction, some of it is in the y direction. Notice that there might be multiple forces acting on this crate, for example, weight and normal and friction, and the person or the forklift that is actually pushing this object. However, we're interested in the work done by friction. So each one of those forces performs its own work. Here, we're specifically interested in the force of friction. Let's start with the green path. We can calculate the work done along this direct path as follows. Work done by friction is equal to the integral of f dot ds. Remember, the dot product is the magnitude of force times magnitude of the displacement times cosine of the angle between those two forces. Also recall that the force of friction can be calculated by taking mu, multiplying it by mg. The displacement is dx, and the angle between those two vectors is 180 degrees. To better understand that, note that for the green path, we're pushing the object to the right, so the displacement vector looks like so. And of course, friction is always opposing the motion. If we are moving the crate to the right, then friction is going to point to the left. That's what the force of friction looks like. And as you can see, the angle between these two vectors is 180 degrees, hence cosine of 180. Cosine of 180, of course, is -1. Mu is given to you as 0.2, m is given to you as 50, g is 9.8. The limits of integration are 0 to 10, because I'm integrating with respect to x. My x initial is 0, and x final is 10. When you perform that integral, you find that the work done by friction is minus 980 joules. Next, let's consider the longer blue path. The blue path is more complicated, so we'll divide it into 3 stages, and therefore we'll do 3 integrals. For stage 1, we'll be moving from our initial position, and we'll be moving along the y direction horizontally. So this is what our displacement vector looks like. And of course, remember, friction always points opposite the velocity. So if you're moving in the positive y direction, then friction is going to point in the negative y direction. So along stage 1, the angle between those two is 180 degrees. So for the first leg of the trip, we have magnitude of the force of friction, which is mu mg. We have the displacement, which is along the y-axis, and we have cosine of the angle between those two vectors, which is 180 degrees, and cosine of 180 is -1. For the second stage of the problem, I'm moving in the x direction, so the displacement vector looks like so. And of course, friction always opposes the velocity, or at least kinetic friction does. So now the direction of friction has changed. Before, friction was pointing in the negative y direction. Now it's pointing in the negative x direction. The angle between the displacement vector and the force vector is again 180. So we have mu mg, which is the magnitude of the force of friction, cosine of 180, and this time the displacement vector is pointing in the x direction. For the third leg, the same thing happens. For the third leg of the trip, I'm now moving like so. The displacement vector points in the negative y direction, and now friction has changed, and it's pointing in the positive y direction, with the angle between those once again being 180 degrees. So for the third stage, the amount of work that's done is mu mg cosine of 180 times dy. Notice that none of these 3 integrals is 0. You'll have to evaluate each one of them separately. You have different limits of integration for each integral, so you have to consider that. Mu mg is a constant, so you can bring that out. Cosine of 180 is -1. When you do these 3 integrals and you add them together, you find that the work done by friction for the blue path is minus 2,352 joules. Now notice that the work done by friction for the blue path is not equal to the work done by the green path. In our previous practice problem, we noticed that the work done by gravity was independent of the path, so it was the same for both paths. But the work done by friction is dependent on the path, so it's different for different paths. Keep this distinction in mind. Having done 2 difficult practice problems, we're now ready to talk about conservative forces. A force is said to be conservative when the work it performs does not depend on the path. Alternatively, a force is said to be conservative when the work it performs is independent of the path. So imagine that we have an object that is going to move from point A to point B. The object can move along many different paths. Here I'm showing 3 possible paths. So the object can move along the direct path, that's the shortest path, I've labeled that as path 2, but it could also move along path 1, or it could even move along a much longer curvy path, which I've labeled as path 3. Now imagine a certain force is applied to the object to move it from point A to point B. For each one of these paths, we could sit down, we could do the difficult integral and calculate the work that is performed. If it turns out that the work done along path 1 is equal to the work done for path 2, which is equal to the work done by path 3, then we would say that the work is independent of the path. We would say that the work does not depend on the path. Doesn't matter if you take the short path or the long path, the work done by the force is the same. In that case, we would describe the force as a conservative force. It turns out gravity is a conservative force. We've already seen that in the example that we performed. It turns out spring force is also a conservative force. In fact, any force that is constant is going to be a conservative force as well. If a force is not conservative, then it is described as non-conservative. We would say a force is non-conservative when the work it performs depends on the path. So if a force is applied to an object to move it from A to B, and the work done along path 1 is not equal to the work done along path 2, and that's not equal to the work done along path 3, then we would say the force is non-conservative. For non-conservative forces, you have to specify the path. You have to specify exactly how you got from point A to point B. Friction, viscosity, and drag are examples of non-conservative forces. In our next lecture, we'll discuss conservation of energy, and to discuss conservation of energy and understand how it is used, we need to be able to classify forces as either conservative or non-conservative. So you will see the utility of these concepts in our next lecture. And that's the end of this lecture. Thank you for your attention.